So the reason that I put these two into these different groups is for the following. If we look at the ice tables for a compound that has a stoichiometry AB as a solid, it's in equilibrium with A plus in aqueous solution plus B minus also in aqueous solution. These could also be 2 plus and 2 minus, 3 plus 3 minus, 4 plus 4 minus. We know that the charge of the cation and the anion is going to be the same, and it's going to be in equilibrium with its salt. If we set up an ice table, the solids don't show up in the equilibrium expression. If we have an initial concentration of 0 and we dissolve X moles of this solid, that means the change in concentration for the A plus is going to be plus X, for the B minus is going to be plus X, and our equilibrium concentration of each of those is going to be X. The KSP for this expression is going to be the concentration of A plus at equilibrium times the concentration of B minus at equilibrium. So our KSP is going to be equal to X squared. And I should say that this is assuming X moles of solid dissolves in 1 liter of solution. So if we say that we have this solid, we're going to dump it into an aqueous solution, and X moles of that are going to dissolve. That means the KSP is going to be, or X moles of it are going to dissolve per liter. That means the KSP is going to be equal to X squared. And that means, and we can set up these ice tables, and everything that has the same 1-to-1 cation to anion ratio is going to give us the same KSP expression. This is why we can group them based on this. Now, if, for instance, we have a compound in the second group that is AB2 as a solid, that's going to be in equilibrium with A2 plus in aqueous solution plus 2B minus also in aqueous solution. If we set up our ice tables to determine the equilibrium concentration of our ions in solution, again, the solid does not have an effect. Our initial concentrations are going to be 0. We dump the solid into the solution. If X moles of that solid dissolve, we get a change in concentration of plus X for the cation and plus 2X for the anion. That means at equilibrium, our concentration is going to be X for the cation and 2X for our anion concentration. So our KSP is going to be equal to the concentration of A2 plus times the concentration of B minus, that quantity squared. If we plug in our equilibrium concentrations of X and 2X, we get a KSP expression that's going to be equal to 4x to the third. The main thing that I want to point out here is when we look at our KSP expressions, this 4x to the third and this x squared right here are different. So when we go and look at this, if we assume X moles of solid dissolves, the molar solubility is equal to X. So we're trying to solve for X in this particular case. When we're solving for X and we're looking at our KSP expressions, we're going to get a different value of X if we use X squared versus 4x to the third. So what we need to do is look at our two groups, and we can rank them in solubility right away for group number 1 and group number 2. So based on looking at the KSP, we can make two conclusions. conclusion number 1 is that zinc carbonate, or ZnCO3, is going to have a greater solubility than cadmium carbonate, which is going to have a greater solubility than silver iodide. And if we scroll back over here to the KSP values, we can look and we can directly compare the cadmium carbonate, we can directly compare the silver iodide, and we can directly compare the zinc carbonate just by looking at those KSP values. We can also directly compare cadmium hydroxide and cobalt hydroxide. So at the end of the day, we can know just by looking at the KSPs, we can narrow it down to 2 particular compounds that we will have to do calculations with. So based on just looking at the KSP, the zinc carbonate solubility is going to be greater than the cadmium carbonate, which is going to be greater than the silver iodide. We also know that by looking at the KSP, that the cadmium hydroxide is going to have a greater molar solubility than the cobalt hydroxide. In terms of comparing these 2 groups, a calculation must be performed. So we need to do some type of calculation in order to determine our molar solubility right here. So we can go ahead and do that. So we know that for zinc carbonate, our KSP is going to equal the concentration of zinc 2 plus times the concentration of the CO3 2 minus. We have a 1-to-1 cation to anion ratio, so we know that our KSP that we saw up here is going to be equal to x squared. The listed KSP is going to be 1.4 times 10 to the minus 11. So our x squared is going to be 1.4 times 10 to the minus 11, and our x is going to equal 3.7 times 10 to the minus 6 molar. This value for x is the molar solubility of zinc carbonate in an aqueous solution. So we can't just look at the KSP and determine that. We have to think a little bit and do a calculation. One of the things that I hope you picked up at the very end of chapter 16 and 17 is that when you're doing these ice tables, the more problems you do over and over and over and over again, you might not have to write out the entire ice table like that. If you see a 1-to-1 cation to anion ratio, you should know that at equilibrium, if we're just in aqueous solution, we're going to get a value of x squared. If you see a 1-to-2 cation to anion ratio, we know that our KSP in this case is going to be 4x to the third. So we can also come back here and look at the KSP for cadmium hydroxide. It's going to be the concentration of cadmium 2 plus times the concentration of OH minus, that quantity squared. And from what we showed earlier right here, that's going to be equal to 4x to the third. Our 4x to the third value, if we plug in the given KSP, it's going to be 2.5 times 10 to the minus 14th. And that's going to tell us that x is going to equal 1.8 times 10 to the minus 5. So now we're able to compare this value right here to this value right here. And we can directly compare them. So we now have the molar solubility of each of these complexes. We can come over here and write that 1.8 times 10 to the minus 5 molar is greater than 3.7 times 10 to the minus 6 molar. And the conclusion then that we can finally draw from all of this is that CdOH twice, or cadmium hydroxide, has the largest molar solubility. Okay? Does anyone have any questions on this entire procedure right here? And one of the things that I want to point out is that if we look back here, this question looks oh so innocent, right? Which of the following has the largest molar solubility? I give you 5 complexes and 5 KSPs. The innocent thing to say, and the naive thing to say, is that, oh, I'm just going to rank them in order of KSP, and that's probably going to be the right answer. I guarantee you that's going to be probably option A or B on a multiple choice exam. Okay? But yes, that might be a trick question, right? But what I want you guys to do is I want you to think these problems through. And I want you to think about what's going on and analyze all the facts that we have at hand. If we come back, I mean, there's a lot going on here. And you need to do the practice problems for this stuff so you can think about these things kind of like the back of your hands. Okay? One of the things that I want to briefly mention right now is we're going to look at, or at least it looks like the bell's going to ring here fairly soon. We're going to look at, when we start class on Friday, criteria for a particular precipitate to happen. So for example, we have this barium chromate. And if we mix 2 solutions together, will a precipitate form? The example I'll give is if we have sodium chloride. A lot of us know that table salt will dissolve when you put it in water. There's a certain saturation point that we can meet. Okay? So when I mix 2 solutions together of sodium and chloride, will a precipitate form? When I mix 2 solutions together of zinc and carbonate, when will the precipitate start to form? And we're going to compare the KSP versus the Q, and we'll start with that on Friday.